10,000 years. Now, you might be thinking that's a timeline for ancient human history, but no, it actually represents the astonishing number of years that data can now survive flawlessly, literally without a single drop of degradation. Welcome to this explainer. Today, we're looking at a breakthrough that, honestly, sounds like pure science fiction, but as you'll see, it is very much reality.
Because right now, we're facing a massive human data crisis. We're doubling our data generation roughly every 3 years, just pumping out information at an exponential rate. But if we look at our current physical storage mediums, hard disk drives, magnetic tapes, they're actually really fragile. They degrade within years, maybe decades if we're lucky. And that means we're constantly forced to migrate data to new media, which just eats up massive amounts of time, energy, and money. We desperately need something better, something permanent.
So, let's dive right into this groundbreaking end-to-end archival solution from Microsoft Research. It's known as Project Silica. And the coolest part? This isn't just some theoretical concept in a lab. It is the very first glass-based data storage system that actually meets all the practical, real-world requirements of a production storage system, seamlessly handling the writing, reading, and decoding.
Here is our roadmap for today's explainer. 1. Project Silica in glass storage. 2. Laser writing, specifically voxels and symbols. 3. Automated reading and decoding. 4. Quality factor and data metrics. And 5. A 10,000-year legacy.
All right, let's kick things off with Section 1, Project Silica's glass storage.
Picture the journey of user data being written directly into a square platter of highly durable glass. Now, this glass isn't huge. It's about 120 millimeters square and just 2 millimeters thick, but it is incredibly resilient. We're talking chemically stable, completely resistant to moisture, immune to electromagnetic interference, and totally untouched by normal temperature fluctuations. The data gets physically etched into this glass using advanced optical systems, and later it's read back out using wide-field microscopy.
Moving right along to Section 2, laser writing, voxels, and symbols.
Before we get into the lasers themselves, we absolutely need to nail down what a voxel is. Basically, think of a voxel as a three-dimensional pixel. A femtosecond laser focuses its energy to create this microscopic 3D modification that is permanently suspended right inside the volume of the glass. The laser writes these voxels in two-dimensional planes, and then it just stacks those planes into massive three-dimensional grids within that 2-millimeter thick glass.
But here's where the engineering gets remarkably efficient. Instead of just holding a simple binary 1 or 0, Project Silica uses what we call a symbol. A symbol is a distinct, measurable physical state within that voxel. So by carefully modulating the laser, a single microscopic voxel can actually store multiple bits of information all at once. It's a real game changer for density.
Now, the laser actually speaks two different dialects, so to speak. The first uses birefringent voxels in high-purity glass. Here, a laser pulse is split into a seed and a data pulse, and the data is encoded by changing the physical orientation, or the polarization, of the modification. The second method uses phase voxels in cheaper glass. This is a simpler method that just uses a single pulse, changing the energy of the laser to alter how the glass refracts light. And both of these methods are blazingly fast, writing up to 10 million times per second.
That brings us to Section 3, automated reading and decoding. So let's assume years, maybe decades have passed. When it's time to read the glass, the microscope doesn't painstakingly look at individual bits one by one. Oh, no way! That would take forever. Instead, it looks at a sector. A sector is a specific organization of tens of thousands of voxels within a single plane, perfectly sized so it can be captured all at once by the field of view of the reading camera.
To actually read the data back, the system relies on wide-field microscopy to capture images of these sectors. It translates the glass, automatically finds the absolute perfect focal position using an autofocus algorithm, and snaps the images. For those birefringent voxels we talked about, it takes images at different polarization states, and for the phase voxels, because the optics naturally stretch the image a tiny bit vertically, it captures images from multiple depths or Z-planes to get a crystal clear picture.
Let's quickly walk through that decoding pipeline and see how this all builds into usable data. First up, the Z-plane images are captured. Second, they go through pre-processing to find the exact boundaries of the sector. Third, and honestly, this is where the magic happens, those images are fed into a convolutional neural network, or CNN.
This AI model has been trained on massive amounts of data to look at the images and infer the correct symbol probabilities, automatically accounting for any optical noise or crosstalk between the layers. And finally, those symbols are mapped back to bit probabilities and scrubbed through a low-density parity check, or LDPC, for error correction. This is absolutely crucial because it ensures total data integrity.
All right, moving to Section 4, Quality Factor and Data Metrics.
So we can write the data, and we can read it back using AI. But to measure success, the engineers don't just look at raw bit error rates. Instead, they track a really specific metric called the quality factor. The quality factor tells us exactly how perfectly the machine learning algorithms can map those probabilities back into the original bit recovery. Basically, it dictates how much extra, redundant data needs to be written to guarantee perfect recovery. The higher the quality factor, the less redundancy you need, which means more raw space for actual user data.
And the numbers here are just staggering. The birefringent system hits a usable capacity of 4.84 terabytes on a single small platter with a density of 1.59 gigabits per cubic millimeter. The phase voxel system, while slightly less dense, allows for much cheaper borosilicate glass and simpler hardware. And check out that throughput. By splitting the laser into 4 independently modulated beams, the phase system scales up to a blazing 65.9 megabits per second, all without causing any thermal damage to the glass. It is just incredibly dense and incredibly fast.
And finally, Section 5, a 10,000-year legacy.
Now, you might be wondering, how on earth do you prove something will last thousands of years without actually having thousands of years to sit around and test it? Well, you use an Arrhenius plot. The research team literally baked the glass in accelerated aging experiments at an extreme 290 degrees Celsius. By carefully tracking the decay of the written structures at those super high temperatures, they could confidently extrapolate the timeline. And they definitively proved these data voxels will remain completely stable at room temperature for over 10,000 years. No degradation, absolutely no data loss.
Think about what that really means for us. We finally have an end-to-end archival technology that completely solves the human data crisis. A technology that literally outlasts entire civilizations, turning our fragile digital footprint into an indelible geological record. So the ultimate question I want to leave you with today is this. Since we now possess the power to perfectly preserve data for millennia, what knowledge is truly important enough for us to save? Thank you so much for joining me for this explainer. I really hope this sparked your curiosity just as much as it did mine.